Yeah.
In fact, I found out the file, but I couldn't fetch that file. I mean, I could not retrieve that file from Wireshark.
Okay. So can you show me that file?
Yes.
Just a second. Yeah. Now you can share it.
Okay. If you look at it, so the line I have selected, or this one, it says that one file, one .png file being transferred from the FTP server to the attacker.
Exactly. So this is the file the attacker downloaded from the FTP server.
Yeah.
Okay. How we can fetch it? You can simply right click on this particular packet and you can follow the TCP stream. Yeah. Actually, I cannot see that window because you have just shared the one window of Wireshark.
Oh, okay. Let me see. Let me see how can I stop sharing. Not sure. Okay, now I'm sharing the whole monitor. Can you see it now?
Yeah. Yeah.
Mhm.
Okay. So here we have the entire communication between the server and the client. And here you can see the client retrieve the why we can't have the cat, a nice cat dot png. It is the file.
Yeah.
So,
Yeah.
and here from the server side, we have the response, which is transfer completed. So what we can do, so there's an option in the below, you can see there's a stream here. Stream 7356, like in the bottom right corner. Bottom right corner.
Yes, yes.
Now you have to press a upper arrow key. Upper arrow. There's a small upper arrow. Yeah. Just wait a second. So this will, now this is the list of all the files which the attacker check out. Attacker apply the list
Oh,
and the server says, okay, these are the list, like these are the files available on my FTP server. Now you can press one more time, upper key. So this will show you again some list of files. In this list of file, we have this one, why we can't have cat.png. Okay, now you can press upper key again.
oh, I didn't know that. So we can see, I mean, in the packet capture, it was not showing all those things.
Yeah, because that is transmitting in the fragments, not at a whole packet. So we cannot see. So that is why
Okay.
now here you can see in this, if you notice, we have this .png file here, this one. So it is a
Okay.
PNG file. So what you can do, you can click on this one, which is entire conversation. This upper
Okay.
key. And you have to select the second one, which is, last one, which is from the server to client. And then here you can click on show data as raw. Show data as raw. This one. Yeah. And then click on save as here.
Oh, okay. Okay. I remember you showed that last time. I couldn't.
Yeah.
Couldn't
So you
now.
can save this file by any name .png.
What's that?
You can save it with any name .png.
Okay.
Save on desktop. Okay, no issue.
Okay.
Yeah,
So
now you can check that file.
Yeah, I see it.
Yeah,
Is
now
it
you can open that file. Yeah, this is the
No.
file. And this is not malicious, it is just an image.
Okay, I get it. I
Okay.
get it.
So this is the file which the attacker fetched from the server. So overall, what we can conclude in this particular scenario, we have a DOS attack. And before DOS attack, there's another attack, which is a brute force attack on FTP server using
Yes.
a password list. Okay, a password word list. And the attacker manages to hack the FTP server and manages to fetch one file. It can be any file. It can be maybe confidential in real scenario. For now, it is a kind of uh, like like mimicking the real scenario. It is not a real scenario, but maybe in the real scenario, the attacker can fetch multiple files. So this is how you can find it, and you can fetch
Okay.
those files in your local machine.
Okay, I get it.
Even the attacker can upload anything on the FTP server. That is like, this is a way you can check. So whenever the attacker is uploading anything or downloading anything, you can see in the FTP-data. That is a FTP data. The rest is a
Okay.
simple FTP communication. Is it clear,
Okay.
the whole scenario?
Yeah, I mean, here, I mean, when we clicked on that upper arrow for the first time, it was showing a few other files. So actually, the client requested for the list of files in the directory, and the FTP server showed that it happened.
Yes, yes, it happened. The client requested for the list of all the files and
Okay.
directories in the current working directory. And the server shared that list.
Okay, I got it.
Okay, so whenever you are finding something, you can simply use this stream ID. This will help you to reach to that location where your
Okay.
actual data is.
Okay, yeah, I get it.
Any other questions from this scenario?
This scenario is clear. And from the last class, I see that, I mean, we went through how to see if there was any packet loss, like, I mean, we are looking at the sequence number and the acknowledgement numbers and all stuff. So it's clear to me, concept is clear to me, but if you can do it in a short time, like, I mean, if you can just explain it again, I mean, that would be, that would be very clear to me. If
Yeah,
it's
I will show you today how we can use that particular mechanism, which is sequence array, to find the packet loss that we will discuss today.
Okay, yeah, we can.
Like how we can check the TCP retransmission and how we can analyze that traffic, which contains TCP error. Okay.
Yeah. Okay.
So now can we start?
Yeah, we can start.
Yeah. So first we can analyze the DNS traffic. Okay, quickly, it is like again a simple protocol. So we can analyze first the DNS traffic, then we will move to the TCP. Okay.
Okay.
So in this file, I have around 9,700 packets. So here we have displayed 172 packets out of 9,000 packets, 9,700 packets. All these are DNS packets. So you know the mechanism of how the DNS is working?
Yeah, I mean, DNS is primarily used to resolve any, I mean, any domain name. I mean, mapping IP address to a URL.
So it is mainly for resolving the IP address to the domain name and vice versa. Okay,
Yeah.
so let's say this is my first packet, which is source, is my system, and this is my destination, which is my router here. Okay, which is we can see our DNS server. Okay, and here we are sending a standard query, which contains a pointer record. PTR is like a pointer record. We have many records in DNS. So PTR is a pointer records. Now, what is PTR? PTR is a basically the basic mechanism of DNS is to convert. Like it is for asking. It is for asking the domain name in place of the IP address. But whenever we are seeing this PTR, this pointer record, then we are doing vice versa. Here we are asking for the domain name on the basis of this IP address. So that is a pointer record.
Yeah.
If I expand this one it is a UDP packet. Okay, we have some information about UDP. Then here we have this DNS information. This is the transaction ID. Now this transaction ID, you will see, this will be unique for each transaction. Means this is a request packet. This one is a request packet. Now when you receive the response of this packet, you will find the same transaction ID here. Okay, which
Okay.
means the packet, which is the request and the response packet contains the same transaction ID, so that we can recognize which response it is, which response it is. For example,
Okay.
here you can see the transaction ID is 0x8B96. Okay, here you can see the same transaction ID where we can find. So we can simply apply the filter. Okay, we can apply the filter here. So we can right click. We can see if we have any response of this packet or not. So we can right click. There's a filter, applies filter selected. Now you can see we have the response with the same transaction ID. You can notice this contains the transaction ID, this one, and this is a packet, and this is the transaction ID of this packet. So remember, transaction ID is mainly for tracking the request and response packet together. So whenever we are finding, let's say we are requesting for finding any domain or for finding any IP, so we can look for that particular transaction ID to find the response of this request packet. If we have the packet, then we can say we have the response. If we don't have the the response, then we can say we didn't receive the response from the server side. For example, here, this is the first request I have made. And here you can see flag here is standard query. Okay, so we have some information. But here, we have this question one, which is first question. And we have no answer, which is answer to the request response. Answer RRS, which is request response. So we don't have any answer in this packet because it is a request packet. Then authority answer is 0, additional answer 0. But when we see the queries, we can see we are requesting for this particular IP address to resolve. So we are requesting for this IP address to resolve, and type is pointer address. It is like a pointer request where we are resolving. We wanted to resolve the IP on the basis of DNS. Class in. Okay, which is internet. Then here you can see the name here. Okay, and you can see the name length. Now, what is this name length? It is like the length of this particular name, including the dots. So 161 is 3.435 and so on. So this is the length of the name. Then we have this label count. So what is this label count? It is like how many partitions are there, dividing the IP address on the basis of dot. For example, you can notice 161 is one partition. Then we have dot. Then 3 is another partition. Then we have dot. Then we have 18 is another partition. Then we have dot. Then 104. Then this part and this part. So if you count, it is 1, 2, 3, 4, 5, 6. So this is label count is 6. How many partitions are there on the basis of dot? Then your type here is pointer record. Okay. Domain name pointer and class A, which is internet. Okay. And here you can notice there's a link up here, which is response in packet number 61. And this is packet number 61. And this is a response from my DNS server to my DNS client. And it is saying that there's no record. Okay, there's an error here actually. Here you can see transaction ID same here again, because it is the response of this particular request. So transaction ID same here. So with the help of transaction ID in the DNS, we can identify the packet loss. Let's say we are requesting to any particular, we are requesting to find any particular IP or DNS, and we are not receiving the response, which means we can track that on the basis of transaction ID. That do we have any response on the basis of this transaction ID or not? Okay. And here you can see we have this flag, which is we have a response here, which is no such name. Then we have this questions, and then with this authority answer, which is one answer from the authority server. That is, this is the query, this is the name and other information. And the answer in the authoritative name server is that. So it is providing some information. So it is providing the information of the authoritative server, but not the exact DNS of this particular name. So here you can see no such name of this particular pointer record, like no DNS name of this particular pointer record, but it is providing the information of the authoritative server. Okay, for example, so it is a like what we can say, SOA, it is a service of authority record, and class in internet. This is a name, M name. Okay, then we have this name here, and type is start of authority. Yeah, start of authority record. Then class in TTL here, date, data length here, and primary name server. So it is providing the information of primary name server. We have primary name server and we have secondary name server. If you remember, primary name server is mainly the main server, and secondary name server is mainly if there's any changes in the primary server, then secondary server will change according to the primary server. Okay, so if you notice here, the primary server is this particular server, Cloudflare. Then responsible authority mailbox is this one. This particular authority, which is here you can see, it is responsible for this particular record, which means whenever you are facing any problem, then you can put a complaint on this particular record mailbox. So that is what it is asking. It is a authority mailbox. Let's say we have any problem, we have any DNS issue, then we can put a complaint on this particular authority. If the issue is from that side, from the server side, then we have serial number here, and then we have this refresh interval. Now this refresh interval, retain interval, and this expire limit, these are related to the secondary server. As I said, let's say we have a primary server. Now primary server is synced with the secondary server.
Yes.
The secondary server will keep on updating if there's a changes in the primary server. So this is the refresh interval of the secondary server, which is 2 hours, 46 minutes, 40 seconds. So the secondary server will wait for the 2 hours, 46 minutes, 40 seconds to refresh again. So after 2 hours and this much time, the secondary server will again refresh. If there's any changes made in the primary server, the secondary server will adapt that changes. Then with this retain interval, retain interval is like when there's no changes, then this much is the time. Let's say there's no changes in the primary server. So the secondary server will wait for 40 more seconds to refresh again. Okay, just refresh. Okay, so it is like in this particular time, 40 minutes, the secondary server will keep on checking if there's any change in the primary server or not. If not, the secondary server will update. Okay, like just refresh. Then this is expire limit, which is 7 days of the secondary server. Okay, and then we have this minimum TTL, which is 1 hour. Then we have this like a packet, which is request in this one. And if you notice, the time here is we have requested at this time, it is the first request, and we have received response after 0.028 milliseconds. Okay, so it is a like a very slight delay of while receiving the response from the server. And overall, we don't have any record of this particular IP address. If you see this IP, I think this IP is 104.18.3.161. It is in the reverse order when you find in the PTI records. Okay, it is in the reverse order. 104.183 and 161.
Oh, okay.
So this is the first request and response, and we can analyze on the basis of transaction ID. Then let's say I am again requesting for this IP address. You can see it is a transaction ID 0x. We can apply the filter first on the basis of transaction ID. So we can apply this filter and select. Yeah, so we have the response again. Now, if you notice here, the IP address I just wanted to resolve is, again, it is a pointer record, is this IP address. This one. Okay. And if you notice, IP is 192.168.0.100. It is not 100.0.168.192. It is in the reverse order. Okay. It is 192.168.0.100. This is the IP I just wanted to resolve. And other information, which is, let's see. Again, the same information, the name length, the label count, like number of partitions on the basis of dot. And it is a domain name pointer record and class in internet. And here we have the response with the same transaction ID that we don't have such name. Again, we don't have any record for this particular IP address. Okay, you can see we don't have any authority server records. It is just a question and we don't have any answer. If you see, answer is 0 in this packet. A simple answer is 0, which is the answer of the resolved domain. Authority answer is also 0. Additional answers are 0. Which means we don't have any information about this particular IP. No authority record, no other records. And IP is 192.168.0.100. So no such name. Okay. And it takes around 0.006 second to receive. Okay.
Yeah.
Now we
Yeah.
can check for any other different packets. This is with the pointer records. Let's say
Yeah.
we have this record, which is, these are all pointer records. We can check this one. It is
Yeah.
a record, which is IPv4 record. Okay. So here we have this transaction ID, flags here, question number one, which is one question in this packet. And we
Yeah.
wanted to resolve this particular domain, which is google.com. Type
Mhm.
is IP address 4. So we want IPv4 for this particular domain. Then class in internet and some other information with the same information. Type A means IPv4. Then we have this response in packet number 134. So we can
Yeah.
double click and we can move to packet number 134. And packet
Mhm.
number 134 contains the same transaction ID.
Mhm.
In this, we have the response from the, you can see, here we have standard query response with no error and question number one. And this is the question number one and answer one. So whenever you find the proper answer of any DNS request, then this answer, this particular flag will become one. When we don't receive any answer, but we have something coming from the authority, then we have authority answers. Okay, so this is a like a answer number one, which is like a actual answer which we are looking for. And in this answer, we can see this is my query, which I am requested, and this is my answer. So question one and answer one. So if I scroll down here, so you will notice we have this IPv4. So this is IPv4 of google.com.
Mhm.
216.5.8.200.195.
Yeah.
Host Google. Okay, IPv4 class internet TTL here and data length here, and this one address here. Okay, and this has received after 0.005 seconds.
Mhm.
This is IPv4 record. Same as we can check out for the IPv6. Sorry, yeah, IPv6. So you can see this is for the HTTP record. This is a
Mhm.
HTTPS record.
Yeah.
Okay, so this is, we are requesting for the HTTPS record. You can see type is HTTPS. So this is a special kind of request, which is HTTP specific service request,
Mhm.
where we wanted to resolve this DNS on top of HTTPS.
Yeah.
And you can see the response in packet number 133. So we can double click on this link. And here we have the response containing the information. So again, we have no error here. Okay, no error. Question number
Mhm.
one. And for this question, we have this answer number one without any
Yeah.
error. This is my question, which I am requesting, and this is my answer. In this, you can
Mhm.
see we have this answer, google.com. And this is type HTTPS in class N. And this is the name, type is HTTPS, other information. And this is service priority. What is this
Mhm.
service priority? Let's say I am requesting for, let's say google.com. Okay, I'm requesting for google.com. And let's say I'm
Yeah.
again requesting for the google.com.
Mhm.
So let's say I'm making three requests at a time. Let's say I'm requesting for google.com. Let's say
Yeah.
google.in or google. Again, any particular domain. Okay, let's say any subdomain of Google. So service priority says first priority is given to this packet, this particular packet, which means whenever, let's say we are receiving three packets from the DNS server, which containing three informations. Like let's say different information of Google. Let's say we have in the first packet we have different IP of Google. In the second packet we have different IP of Google. Let's say of any subdomain, and let's say we have different IP of Google for any C name. Okay, any other name of Google. Okay, like alias of Google. So now here service priority says first priority will be given to this particular packet, which means to give to this particular domain here. That is service priority. Okay, it is like just priority. It is flagging this packet as a first priority packet. Because it is saying that whatever you are looking for, first look for this packet or check for this packet. Okay, and target name is root, and here you can see with some service parameter. Now service parameter says us, if I expand, see in the service parameter we have some information. First containing the alpha. Okay, not alpha, sorry, alpha, this is some alpha number which is h2 and h3. H2 is h and h3, these are the versions of the https which is supported by the Google. Okay, so Google can support http2 and http3. Okay. Then with the
Yeah.
service parameter key name is ALPHN, and the parameter value 6. ALP and length is 2. So it is supported by H2 and H3. So this is the version. This is like the version. The Google is telling us that I can support HTTP2 and HTTP3. Okay. So this is what is service parameter is. Okay, this is important. Service priority and service parameter. And target name is root. We are requesting for the main Google server. Okay. Now, this is HTTP record. Now we can check for any other record, which is IPv6 record. So, do we have any? Everything is here as a pointer record, and maybe there's a packet which contains some string function. Let's see this. The same function. These are all the HTTP. Oops.
Okay.
This is IP. Yeah. In this factory, you can see. Let me apply the filtering on the basis of transaction ID. Okay. Okay. Apply. Here we are requesting for this particular domain. Okay, which is standard query is to resolve this particular domain. It is a IPv4 record. Okay, a record. And we are requesting for this particular domain. This one. So length is this one and label count is 4 because we have 4 partition. First partition is beacons, then GCP, then this one and .com. So we are making partition on the basis of dot and type IPv4 and class in means internet. And here you can see the second packet. We have some more information, which is first standard query is no error. Question. Now here you can see we have 2 answers of this particular query. 2 answers. Okay. First answer says, first is the question, and 2 answers says, first is providing you the 2 names. First, the canonical name, which is CNAME record. CNAME record. And second is providing you the type A record. What is canonical name? It is like an alias of this particular, the main domain. Okay. For example, we can have alias. For example, we have google.com. We can have gmail.google.com. It is again an alias. Or we can say we have this www.google.com, or we can have simply google.com. So a user can request multiple, he or she can request any domain in multiple ways. So we have alias here. So CNAME is for canonical name, and it is a kind of a alias. So it is this answer is from the CNAME record. And it says, and here you can see we have this name here, and CNAME is a canonical record, and this CNAME here, which is speakers -handoff dot GCP dot this one. Now you can notice here the actual domain which we were requesting is this one here, which is beacons.gcp.gvt2.com. But here we are receiving the response with the CNAME beacons-handoff. So this -handoff is a canonical name here, because actually we are requesting for this particular domain. Okay, but we have another canonical name for this particular domain, and this is the canonical name. Okay, so we have the response from the first as a canonical name, and second as the original name, which is this one. It is a IPv4, and we have the information, which is this is the IP address. This is the IP address of that canonical name. So first, it is telling us that I am providing a canonical name of this particular domain, and this is the IP address, which means if a user visits this URL, or if the user visits this URL, they will land on the same IP address, which is this one, 142.250.194.9, which is provided by the server. Okay, so either the user can visit on this particular URL or on this particular DNS. They will end up on the same IP address. That is what CNAME says. Is it clear? The CNAME?
Yes, sorry, it was on mute. Yeah, it's clear.
Okay, now we can check out just DNS response. Okay, let's see if we have any other. So these are the packets which contain two answers in each of this packet. Okay. So let's see if we have any other answers. So here we have again the CNAME. Okay. So these are all CNAMEs here.
Mhm.
This is again a request which contains around two questions. So we can append this transaction ID on this packet.
Mm.
So we have here we have this DNS request here, which we wanted to resolve IPv4, and this is the domain messaging.engagement.office.com. Okay, this is my DNS which I wanted to resolve. And here we have this response, and you can see there's a delay in the response of 0.362 seconds. There's a delay.
Okay.
And this also response contains two answers. First answer is, let's see. So first is a question, and then we have two answers. Again, the same answer. We have the CNAME here, and then with this IP address of that CNAME. Okay. So the most common records we will find in the DNS is CNAME, the IPv4, IPv6. For the IPv6, we will find 4 times A. 4 times A. That is IPv4, IPv6. For the IPv4, we will find 1A, and rest we will find the CNAME pointer records, IPv4, HTTP, and 4 records. And something like SOA records, which is start of authority records. Okay, so these are like common records we can find in the DNS. Is it clear?
Yeah, that is just clear.
Okay. Any questions from the DNS, like any additional question?
DNS is fine. This one is just fine.
So now we can move to the TCP. Okay.
Yeah, just before starting TCP, just a common question about the time displayed, because I just tried something and I could not make it. So here we know the if you look at your screen, the number. Okay, that's just the number. We have the delta time displayed. That is the time between the previous packet. So let's say if you have to follow one stream, just communication about one sequence, one transaction ID. Like, if you're looking at a bigger packet capture file, we see a lot of communication taking place. So if we filter it to the traffic from one particular customer to the server, then how will be the time displayed?
So you wanted to filter on the basis of a one communication between the server and the endpoint, two endpoints.
That's right. Yeah,
Okay.
that's right.
Then on top of that, you want to analyze time delays, right?
Yeah.
Okay. See, let me open a packet. Let's say, can open. So in this file, we have many packets. Okay, many TCP packets. Let's open the conversations. Okay. Here we have this TCP here. Now let's say we have many IP addresses. Okay. Now let's say I just wanted to apply the filter on the basis of one communication. So either I can apply from here, and I can apply, or I can apply from here. Let's say I just wanted to apply on this particular communication, which is history.google.com. So I can right click, and first I can apply a filter TCP. Okay. So now this is a filter which will provide us the communication between my machine and this google.com. One endpoint and the other endpoint. And here you can see, we can simply click on view, and we can change the time to delta time displayed, which is seconds since previous displayed packet. Okay. And here we can simply arrange these packets in the ascending order first. Okay, 262, 266, these are all in ascending order. And here we can simply analyze the time delays. For example, this is the first packet sent by my machine to this google.com, and it is an egg packet. Okay. And then second communication is 0.083. After 0.083 seconds, the Google respond me with egg packet. Okay, again egg packet. Then after 16 seconds, there's a delay here of 16.184 seconds. Approx 16 seconds, my machine send the packet to google.com, which is a FINET packet. So whenever we are terminating the connection, there's a delay, and that delay is common. Okay, that delay is common here. So we are terminating after 16 seconds. And then we receive the response from the Google after 0.83 seconds. You can see if we notice the Google response is same, 0.083 seconds and again 0.083 seconds. So it is like a, we can say a delay, like a common delay, or we can say a common time taken by the Google to send me the reply. Okay, which is same here, 0.083, and the second reply is also after 0.083, and it is a FINET packet. And then we send the egg packet. So, and hence the connection is closed here.
Okay.
So this is how we can analyze the time delays.
Okay, so if we filter out something, and so the new window, the delta time displayed on the new window is adjusted to the new output, right? Not the old output.
Means?
I mean, now, okay, I mean, in this window, the delta time displayed is between these packets, not the old ones.
Yeah. Yes.
Okay. Yeah. That's what I wanted to. Because I mean,
that is like,
in my situation, I mean, we have got only one server sitting in the data center which capture all the traffic. You know, so different people are using this server, so I need to do a lot of filtering. I mean, I tried to filter it, and it's a huge file. So I had to do that filter. So now I get it. Yeah, that's fine now.
Okay. So see, whenever you are analyzing delay, this mechanism will remain same in every sort of protocol you are analyzing, which is delta time display. It is like a very powerful mechanism, and it will show you the actual delay between the packets after you apply the filter. Okay. Before applying filter, it is same as captured time. But when you apply the filter, then it will become a different time, and will show you the actual actual delays between the packets. Okay.
Yeah.
So is it clear?
Yeah, that's clear.
And with this one, also we can see the that cumulative time, which is like how much time like this packets or this conversation takes, which is like we can simply click on the click on view, and here we have this time display format, and here we have this seconds since first capture packet. First capture packet. Okay.
Yeah.
So here now you can notice there's a 6 second. Okay. So the timing is starting from 6 second. So when we are capturing the packet, on 6 second, we capture this packet. Okay. On 6 second.
Yeah.
6.780. Then 6.864. This is another way of analyzing packet delays. You can subtract these timing, which means if you subtract, let me show you, 6.864, which is 6.864 minus 6.780 minus 6.780. You will notice 0.084 delay, the same delay which we were having, which means if I add a window for the delta time displayed, you can see.
Yeah.
Approx 0.084, the same timing here, which means this delta time is showing you the delay. Okay. This one is showing you the packet delay between the previous packet and the current packet. And this you can be sure with the help of using the second since first capture packet. So basically this particular packet, this single packet is showing the delay between the first packet and this packet number 262. So there's a delay of 6.780 seconds. But if we analyze the delay between 262 and 266, then we can simply subtract and we can find there's a delay of 0.84 seconds. The same delay we can see here in the delta time displayed. Then you can see there's a delay. Then after 23 seconds, on 23.079 seconds, we share this packet. So we can simply subtract 23.049 minus 6.864. 6.864. 16.185. You can see it is approx 16.185. So this is our delay. Okay. And if you find the actual duration from starting to end, then you can subtract this timing with this timing. Okay, which means we can subtract 23.134 minus 6.780. 6.780, which is 16.354 seconds. So this is the whole duration taken by my machine and this Google to finish up the entire communication. Okay, 16.354. It is like a duration of this communication. How long this duration start and ends. Okay, like how long this duration flow. So it is like 16.354 seconds. So within 16.354 seconds, this duration starts and ends.
Okay. Yeah.
Is it clear?
Yeah,
For analyzing the entire duration. The same duration, if you see that same thing, you will see here in the statistics conversations. So you will see in the IP TCP layer. See, the same timings you can see the duration. 16.353. Okay, the same we were having. So this is the actual duration taken by the server and client to start and end the communication, the total duration. Okay, and this is relative start time. If you see this time, relative start time is same as 6.7 this time, which is first time. Okay, this is a relative, which is a cumulative time here. Okay. And more else, let's see if we have any other timings. So relative start we have duration. Yeah, that's it. Okay, so these are the time you can see from here also.
Yeah, how we got this output? By clicking on the statistics of that packet, right?
Sorry?
How we got this output? By clicking on the statistics button.
Statistics. First, I have applied a filter. Okay, to filter on the basis of source and destination. Only this communication. Then I click on statistics, conversations. Then you can notice there's a point here which is limit to display filter. So this option is tick here, which means this will only show me that communication which is on my display option. And here I click on the TCP because I know it is a TCP communication. So here we have. Even it is a IPv4 communication also. Okay. And even it is a Ethernet also, where a MAC addresses are communicating on the different layers. But we are actually analyzing the TCP packet. So we will see TCP here. And if I remove this filter, here you can see, we can see the entire communication of everything. Okay. But if I apply a filter here, you will notice the time here. Even we can see a graph here. Graph. Of this particular communication. It is like an input and output graph. So you can see at y-axis we have sequence number and at x-axis we have time here. Okay. So we can just zoom out a little bit so we can find packets. So these are the packets you can see. So it is in middle of 0 to some 200 milliseconds here. You can see. And there's a sequence number. It is going from 0 to maybe you can see there's a line here from, you can draw this line up to here. So it is like around maybe 50 something secrets number. Okay, 50 something. So we can also see this in the like graph. It is like a new feature in the Wireshark. Previously, it was not there. It is like I think it is a new feature. Like where we can plot the conversion on the graph. And the sequence number is going in the middle of 0 to 200, which is in the middle of 0 to, I guess, 50. The same we can see here. See, the sequence number input convolution and use the google.com. Okay, let's apply the figure. Right. Can see first. Um, let's see this communication. So here we can check out timings here of, we can click on conversations and we can click on TCP. Let's see. So the duration of this particular communication from start to end is 274 seconds. So it lasts 274.8 seconds. And relative time is 46. The same we can see in the graph. So these are all sequence numbers and these are the packets. And this is the highest sequence number. So we can check out here that it takes around maybe, I don't know, like 25,000. In the middle of 0 to 25,000, we have sequence number of this packet. So what we can do, we can check here. We can check the last sequence number. You can see it is 13,000. 13402. This 1000. The same we can see the input graph, which means so same we can see the graph here. It is saying the highest sequence number goes in the middle of 0 to 25,000. So we cannot exactly see, like there's like maybe 13,000 or something. So we can zoom in a little bit to check the exact sequence number. Like you have to zoom a lot. Okay, maybe you can see it. Okay, so here you can see it is like it is showing the sequence number, the highest sequence number in what time. So the highest sequence number is in the middle of 150 to 200 seconds. Okay, and the sequence numbers goes like 30,000, like the highest sequence number. So that we can see in the sequence, like in this graph. Okay. Is it clear? Like it is like just checking for the sequence. Okay.
Yeah, it's clear. It's clear now.
Now we can analyze this file for the packet loss and packet delays. So as you can see, this file contains lots of errors and it only contains 32 packets. So the first packet is from this IP, which is 101.1.1.101. And it is a SYN packet. Okay, it is good. Then we have the SYNAC packet and then we have ACK packet. So it is a simple three-way handshake without any problem and without any actual delays. But when let me check the delay time here. Yeah, it is okay. Then we have my machine, which is this client sends the client hello packet. Okay, client hello packet, which contains 214 of data. Okay, the TCP length is 214. Then after 0.307 seconds, this client again shares a TCP retransmission packet. Okay, a TCP retransmission packet. And you can see, let me add another time here. Let me add one more time, which is second since first captured packet. It is also important. Let me add a delta time display also. So this time is first captured packet. Okay, this is first captured packet time in the like from the first captured packet, and this is the delta time.
Yeah.
Okay. Now we can arrange in ascending order again, and yeah. So we have this SYN packet. Let me remove this protocol for now. This all. Then my machine sends. See, after waiting for 1 second, like 0.165 seconds from the first packet. Okay, like you can think of it as an ideal time. Sorry, not this one, 0.472 second. So this is maybe an ideal time for waiting for the client, sorry, for waiting for the server to send the response. And if I didn't receive the response, then I can share the TCP retransmission packet. Okay, which contains a push ACK packet. See, so you can see this is the ideal time for waiting for the client to again send the packet to the server. Okay, so this is the ideal time. How it is an ideal time? Because you can see it is a time between the first packet and packet number 5. So maybe see, after like waiting for 0.472 seconds, my machine, which is the client, sends the TCP retransmission packet. Okay, which is like in the actual delay, it is the actual delay after waiting for 0.307 seconds. So what this packet contains, if we see here, you can see it is a TCP retransmission packet which contains the same data as the client hello packet. You can see 214. So it is a push packet, which is a push flag here, and it is saying it is a push flag here which contains 214 bytes of data. And here we can notice sequence number is 1 here and ACK packet is 1 here. Okay, which is sequence number is 1 here and ACK packet is again 1. Acknowledgement is understandable, which is 1 here because we have only received 1 packet from the server side. But sequence number is 1 here. That is a kind of suspicious because you can see I have already sent 214 of data. I have already sent, but again it is showing in the next packet it is showing 1 packet only, like 1 sequence number only. So it is like a kind of suspicious here. So we can like flag it. We can just what we can do, we can mark this packet for now. Or we can just put for now we can put a packet comment here so that we can analyze it later. What is a packet comment? So we can add a comment here that let's say the client has sent 214 bytes of data already. But in this packet, which is TCP transmission, TCP transmission, it is showing sequence number 1, which, so instead of, let's say, instead of sequence number 215. Why 215? Because I have already sent 214 of data plus one packet previously. So it makes
Okay.
up 215. But here I am like here the sequence number is 1 year, which means
Yeah.
this packet is again sending the client hello packet. You can read. It is
Oh,
saying
okay.
that it is again sending the client hello packet. Okay, which means after waiting for this much amount, my client sends the packet again because it doesn't receive the response from the server side. So it is a TCP retransmission packet again sending. Then after
Okay.
0.090 seconds, my the server send me a packet which says length is 0, which says TCP previous segment not captured. And if you notice, the CPS number is a kind of suspicious here.
Yeah.
You can see CPS number is why it is not showing the entire data. Yeah. So you can see CPS number is in this packet is 4067 and 215 is of length. This one. This one.
Yeah.
Which means the server is saying that I have already sent this much amount of data and received 215 of data. Which means the client has received the client hello packet finally. Okay, it has received the client hello packet. That is why we have this 215. Okay, but it is saying I have already sent 4027 of data, which we haven't received. We don't have received this much of data, right? Because we don't have that packet anywhere in the file. So we have not received this much amount of bytes, which means there's a packet loss in the middle of this packet and this packet. There's a packet loss here. Okay. Is it like clear why there's a packet loss and how we are analyzing it? So there's a the server is saying that I have already sent 4067 bytes of data to you, but we haven't received that data, right? We haven't received that data. So where the data goes, where the packets are, where the data is. So that is a packet loss. Okay. And acknowledgement number is kind of fine here because the machine has sent 214 of data, the client, plus 1, which is 215 of bytes. That is okay here. Which means, which we can see here, here we can again create a packet comment, right? So we can say here up to here, the server receives 215 of bytes. 215 bytes, which is okay. Which is okay. Why? Because we have already sent in the client hello, we have sent 214 data plus 1, which is 215, right?
Yeah.
And but server says CPS number, which is 4067 bytes of data has sent, but we haven't received that data. Okay, that is like a flaw here. So there's a packet loss. Okay, understood this much? So now you can see here after packet number 6, we have packet number 7. And you can see there's a delay of 2 seconds. There's a delay of 2.030 seconds, very high delay. And after 2.030 seconds, we have the server sent me a packet which containing 536 amount of data. 536. And it is a TCP retransmission data. Okay. And here you can see in this packet, the CPS number is 1 year. Why? And ACK is 215 year. How is it possible? How is it possible? See, before this packet, we are having the packet from the server side, which says, I have already sent 406 8 of 4067 bytes of data. But in the
Yeah.
next packet sent by the server, it is saying I have sent just one packet, just
Yeah.
one packet. And
Mhm.
ACK is 215. So ACK is okay here, but
Mhm.
there's a packet loss. Now, what kind of packet loss it is? Like which packet is missing here? You can notice here, we are missing the client. We are sharing the client hello packet, but
Yeah.
there's a missing of server hello packet. There's a missing of server hello packet. And you can see this packet. This packet is saying that I have sent the server hello packet to you, but you haven't received it. And why? Because we have the client doesn't receive that server hello packet. So the
Mhm.
server is sharing the TCP retransmission packet saying that I have already sent the server hello packet, but you haven't received. And you
Mhm.
haven't, if you haven't received, then you haven't acknowledged me. Okay.
Mhm.
And that is why I'm sharing the TCP retransmission packet,
Yeah.
which means, let's analyze it. We have a client here, we have a server here. Client sent the client hello packet to the server. Okay.
Yeah.
But after waiting for, let's say this 0.472 second,
Yeah.
client sent a TCP retransmission packet again,
Mhm.
which containing the client hello packet again. So we have this
Okay.
client hello here. Okay.
Yeah.
So after waiting for some time, the client again sent the client hello packet in this packet. I'm talking about this packet,
Yeah.
which is a TCP retransmission packet. So the client
Mhm.
says that I have already sent you the client hello packet, but you didn't acknowledge me. So that is why
Mhm.
I'm sending the TCP retransmission packet again.
Okay.
Okay.
Yeah. Mhm.
Then we have received a response from the server side, which is a
Mhm.
egg packet. Okay, a
Yeah.
egg packet, which is saying that I have sent this much of data, this much of data, but we haven't
Okay.
received that data, which means
Mhm.
server is saying I have already sent server hello packet to you, but you
Mhm.
haven't received it. Okay,
Yeah. Mhm.
that is what it is acknowledging. So that is why in the next packet, in this next packet, packet number 7, the server is again sending the server hello packet, stating that I have sent the packet, server hello packet of
Yeah.
size 536,
Mhm.
of size 536. And the size, and it is a sequence is 1 because it is a server hello packet which is meant to be sent by the client. Sorry, after the client hello packet. So that is why
Mhm.
sequence number is 1 here. See, if
Mhm.
I show you the the ordinary client hello packet, the TLS connection.
Yeah.
See, it is like you can find easily, you will find the difference. In the normal communication, we have client hello packet, we have the server hello packet. Okay, in the
Mhm.
normal communication.
Yeah.
So, and whenever we are sharing the egg packet, we have the sequence number 1 here. 1 and egg is 191. This packet, this
Mhm.
packet,
Yeah. Yeah.
you can see. Sequence number 1 here and egg is 191.
Yeah.
So this is the same packet you are seeing here. The same packet we are seeing here. This packet. Where it is this packet.
Oh,
Which
okay.
means this is the acknowledgement packet of packet number client hello.
Mhm.
But this containing some data, which means the server is saying that I have already sent you the server hello packet, but you didn't acknowledge me. That is why
Mhm.
I'm sending it again with the TCP retransmission packet.
Yeah.
And it is
Yeah.
a sequence number 1 here.
Mhm.
But in the previous packet, the server is also saying that it has sent 4067 of data already, which is missing in this file, which is missing. Okay. So clearly
Mhm.
we can say there's a packet loss. And what kind of packet loss it is? It is a TCP server hello packet loss.
Hello,
Okay.
hello, packet. Yeah. Yeah.
Is
Yeah.
it clear? Like
Yeah. Okay. Yeah.
analysis?
Yeah. That is clear.
Then on packet number 8, you can see my client, the client sent the server a packet which is an egg packet. And it is
Mhm.
saying, now it is saying the client is correcting the server that I have only received packet 537 of data, which is I have only received 537 data, this much of
Mhm.
bytes, and I
Yeah.
have sent 215 of bytes. So the client is correcting to the server that I have sent 215 of data, which is okay, but I have only received 537 of data. Why 537? Because 536 plus 1, 7. 1 because
Oh,
of previous data. So that is what client is saying, that I have not received any of these bytes, I have only received 537 of data from your side. Okay, so don't say that you have sent 4067 of data. Okay. Then after waiting for, see there's again a TCP retransmission packet. After receiving this packet from the client side, the server says after 0.78 second, again send TCP retransmission packet. And these are all server hello packet. It is saying that why are you saying that you have received 537 of data? I have already sent you this much of data. So where's the data is? So that is why the server is saying, it is saying that I have sent you server hello packet 2 times. This one and this one. And here you can see the sequence number is 537. Okay. It is a egg packet. So this is the acknowledgement of packet number, previous packet number, this one. Because you can see the sequence number is 537. So the server is saying, okay, first thing I have sent you 537 of data. That is okay. But here the server is again saying that I have sent you 1073 of data. This much of data. Now we can calculate if the server is saying right or wrong. So we can open the calculator. See, server is saying that I have sent you 1073 of data. But what we have received is 536 plus 537, right? 537 plus 536 again, right? This much. 537 plus this much data, 537. So here 537 plus 536. How much? It is 1073. Which means this is also right. There's no packet loss here. Why? Because my client has received first 537 of data from the server, then plus 536, which is 1073. Okay. So server is saying I have sent you 1073 of data, which is actually true. Okay, which is actually true because we have received. Then in the second packet, so with this packet, the server shared 536 of data again, which means 1073 plus 536 more, 1609. And the same packet you can see here, 1609, this one. Okay, which means the client is saying, okay, now finally everything is sorted out. I have received 1609 of data, which is actually true, and sent 215 of data. Okay, so now there's no packet loss. Like they keep on acknowledging themselves. Okay, back and forth, they keep on acknowledging and sending data. Okay, then again there's a lots of packet loss here. The client says that I have sent you 2154 of data. Okay, which is, if we calculate, now again there's a packet loss. Okay, there's a packet loss here. If we subtract 2154, 545, there's a loss of 545 bytes. You can see there's a loss of 54 bytes. Because again the server is saying, I have sent you this much of data, but what I have received is this much of data. So if you subtract, you will see there's a loss of 545 bytes. Okay. Again, there's a loss. And if I check out, if we can see the delay here, there's a delay of 0.84 seconds. Then the client sent a duplicate packet, egg packet, which says, see, this is a clearly a duplicate packet because this packet and this packet are same only. These packets are same. Okay, which means this packet and this packet, they are same only. You can see the CPS number and egg are same only. So clearly it is a duplicate egg packet. So now if you think of what is the actual problem is going here, what is the actual root cause of this TCP retransmissions or packet loss? See, server is not receiving the packet from the client side. Okay. And client is also not receiving the packet from the server side. That is why there's lots of TCP retransmission packet between the server and the client.
Yes.
Right. And now this one more thing, that the client is sending the duplicate packet to the server, which means the client is not actually receiving the packet from the server side. That is okay. That is we analyze. But the server is also not receiving the packet from the client side, which means one thing we can say that we can just assume, okay, we can make an assumption here, a theory here, that there's a problem with the client side. There's a problem with the client side. Why? Because if we see in the studying,
Mm-hmm.
if we see in the studying that there's a that it is the server, it is the client first who share the TCP retransmission packet. Okay, it is the client first, which means the client is sharing the packets, and in the middle of anything, like in the middle of TCP retransmission,
Mm-hmm.
when we are sending the client hello, the client again send a TCP retransmission packet, which means the client doesn't receive the response from the server side. That is why it
Yeah.
is sharing the TCP retransmission packet. So maybe there's a high traffic at the client side. Maybe. I'm not sure. Okay. We are not sure for now.
Yeah.
Okay. For now, client doesn't able to receive the packets from the server side. That is the problem. That is why
Okay.
there's a lots of retransmission is going on.
Oh.
But if you notice, we have lots of retransmission packet from the server side now. And then we have
Mm-hmm.
the duplicate packet from the client side, which means client is thinking that I am sending all the packets. Okay. And server is thinking I am sending the packets. There's a problem in the middle of somewhere. In the middle of
Mm-hmm.
somewhere, that servers keep on sending the packets and acknowledging. And client is keep on sharing the duplicate packets of the
Mm-hmm.
previous packets.
Yeah.
Okay, of the previous packet. Now you can notice this duplicate packet, this one. This
Yeah.
packet, these two packets are again the duplicate packets of this packet, which is packet number 11. This one,
Mm-hmm. Yeah.
which means the client is stuck at one place only. Client is
Mm-hmm.
keep on acknowledging and even sending the duplicate packets, which means client is not receiving any of the packet from the server side. That is why it is
Mm-hmm.
keep on sending the duplicate packets. Client
Yeah.
is thinking that my packets are not reaching to the server, right?
Mm-hmm.
So that is
Yeah.
why it is keep on sending the egg packets up to here.
Mm-hmm. Yeah.
So there's
Yeah.
a problem with the client side. There's a problem
Mm-hmm.
with the client side.
Yeah.
Maybe I'm not sure, because with the single picker we cannot analyze the actual problem.
Yeah.
We have to look for the server side also. That what
Mm-hmm.
is going on the server side.
Yeah.
See,
Yeah.
this is the interpretation we are making from one side only, from the client side, not from the server
Mm-hmm.
side. So
Yeah.
for
Yeah.
finding the actual problem, for to be fully sure, we have to
Mm-hmm.
also analyze the packet from the server side. We have to check
Okay.
if the server is also behaving like this or not. Okay,
Okay.
then only we can make the assumption. Then we can conclude that what is the actual problem.
Okay.
Because we cannot analyze the problem only by seeing the one side. Okay,
Mm-hmm. Yeah.
so here the server is keep on sending the retransmission packets, and client is keep on sending the duplicate packets. At last, at last,
Yeah.
the client again sends the duplicate packet. Maybe there's a problem with the client traffic. There's like lots of traffic at the client side. That is why client is not able to send the packets, and that's why it is keep on sending the duplicate packets. Okay,
Mm-hmm.
that
Yeah.
can be a one problem. Okay, one of many problems. Then at packet number 19, if you see that there's a even if you notice one more thing, that there's no delay here. There's no
Mm-hmm.
delay
Yeah.
here.
Yeah.
Here,
Yeah. Mm-hmm.
there's no delay. There's no delay from the server side. Means the servers keep on launching the packets, keep on launching the packets at the client side. And what
Mm-hmm.
client is doing? Client is simply sending the egg packets, which means
Okay.
there's a like a
Yeah.
fast retransmission of packets. There's no delay here, which
Mm-hmm.
is what we can say. There's a packet, there's a high delay. There's a high delay at the there's a high traffic at the client side. Why? Because see, the server is
Okay.
keep on sending the packets. The
Yes.
service keep on sending the packets in the flow without any delay. But
Yeah. Yeah.
because of the high traffic there's a high traffic at the client
Mm-hmm.
side. Because of that high delay, because of the high traffic, the client is receiving the packet,
Mm-hmm.
uh, like a packet as a TCP retransmission packets.
Mm-hmm.
Okay, which
Yeah.
means even we cannot say that there's a high delay, because one more thing is there's no delay here. There's no delay here, which means
Okay.
client is collecting the packet as in the flow. There's no delay, there's no receiving delay from the client side. So
Okay.
what can be the problem? Uh, what can be the possible problem here is there's like lots of retransmission packets and yeah. So because we are recording from the client side, right? We are recording from the client side and there's no delay here. Why receiving the packets from the server side? See, so which means the client is actually receiving the packets. But if we notice previously, there's a delay here of 2 seconds by the server.
Yeah.
Okay. So what we can say maybe there's a problem with the server side. Server is not receiving our packets. Server is not receiving the packets. That is why servers keep on sending the retransmission packets. And because of this retransmission packets, the client is keep on sending the duplicate packets that I have just received this much of data. So there's some kind of problem in the middle because server is sending the packets in the right flow. Receiver is also receiving the packets from the right flow without any delay here. You can see there's no delay here. But these are all TCP retransmission packets without any delay, which means the server is receiving, sending the packets without any delay, and client is also receiving the packets without any delay. But there's a problem in the middle of somewhere, and client is client is sending the duplicate packets again and again, which means client cannot recognize these packets. Okay, which means from these duplicate packets, why a client will share the duplicate packets to the server? Because the server is not acknowledging those packets, right? The server is not acknowledging these packets. That is why it is again sharing these packets, which means the server, it is the server who is not acknowledging the packets in sequence. That can be the issue. Okay, that can be the issue. And then you can see after some time, after everything is okay now, there's some suspicious spurious retransmission packets. That is okay. And then again there's a duplicate packet sent by the client, which means the server is not acknowledging the packets sent by the client at one time. That is why client is again sending the duplicate packets in the hope that it will receive the acknowledgement packet of this particular packet. Anyways, but after some time, everything goes to normal. If you see, we have the client key exchange packet sent by the client. Then we have this change cipher packets, which is normal in the TLS communication. And then we have some data here. And then we have this FIN packets. So everything goes to normal, but in the middle of this one. So I can say that I can just make an assumption, okay, that maybe there's a problem with the server side. Server is not acknowledging the packets in the sequence, which means server is not receiving the packets in the sequence. That is why it is keep on sending the retransmission packet and client is keep on sending the duplicate packets. So maybe there's a sequential issue. And why it can be the issue? Because maybe there's a high traffic at the server side, maybe. Okay, or it can be any other reason.
Okay.
But for now, we can just make some assumptions here. We cannot conclude or we cannot find the root cause without analyzing the server side also. Once you have the file for both server and the client, then you can find the root cause. Like what is the actual problem? Okay, it is like a one-side interpretation. We have to do the both side interpretation of the packets. Then only we can find the root cause. Okay.
Yep.
Overall, we have to you have to analyze in this way only. Okay, just keep on checking the packet delays and sequence and add packets simultaneously. Okay. Like, is it clear? I know it is like kind of complex or confusing. I don't know, but this is the flow.
Okay, yeah, that's fine. I mean, it's okay. It's okay to me.
So if you have any file containing some errors, you can also share it with me. Okay, we can analyze that file also.
Oh, okay. Yeah.
Then you can see we have everything in flow. So the sequence is this much, and it's like everything is going here in flow. So there's no error here. So after some kind of error, everything goes to normal. So this is how we can analyze packet loss and packet delays. Is it clear that communication?
Yeah, that's clear to me. That's fine.
So next we can move to HTTP.
Mhm.
So first we can see how we can decrypt the HTTPS traffic. Okay.
Okay.
HTTP is mainly for the hypertext transfer protocol, and it is mainly for transmitting the data over the websites. Okay, for the websites. So the purpose of the HTTP is to provide a standard way for the web browsers to communicate. So we have this common URL, and we can also use, we will see, we can use these filters for analyzing the HTTP response code, which we have already discussed, right? Then we have the difference in the HTTP, HTTPS, and HTTPS. HTTP, you can see it is a normal communication, okay, which is unencrypted. HTTP2 is encrypted, which is HTTPS. Now we have this HTTP3, which is something different. HTTP3 is working on the UDP protocol, and UDP is like HTTP3 is based on the QUIC protocol, and QUIC protocol is like a combination of TCP and UDP both. Okay, so QUIC protocol is working under UDP, first thing. Second thing is it is different from UDP. Why? Because QUIC protocol is taking some of the features, some of the qualities of the TCP protocol. It is like the developers wanted to make a protocol which contain the qualities of both TCP and UDP. In the TCP, the QUIC protocol takes congestion control, automatic retransmission of packets that UDP does not have. And from the UDP, it is taking the speed of the UDP. Okay. So QUIC protocol is like basically it is working under UDP, but it is like a combination of TCP and UDP. We can say that. That is HTTP3. And many websites are using HTTP3. And QUIC protocol is developed by Google. And it is like, I think, under development. It is like keep on updating.
Okay, yeah.
So first we can see how we can analyze the HTTP traffic. Okay. It is very simple to analyze HTTP traffic, right? Let's say, let's open a in this file. We have HTTP traffic. So it is a simple HTTP traffic between this client, this server, this client, and this server. So we can apply the convolution filter.
Yeah.
Now this is the communication between one client and one website. Okay, same as you can apply any convolution filter to check out the HTTP traffic between the one website and one client. So first with the SYN packet, SYN egg packet. Then the client click on this page, get login.php. Now what is this get here? See, we have this two request. It is a PHP request, get and post. Basically, we have four types of requests: get, post, put, and delete. Okay, we have four requests: get, post, which is post here, and put and delete. Put and delete is mainly used in the development. So whenever we are uploading anything, we use put. Whenever we are deleting something, we use delete. But get and post is something very used very commonly. Okay, let me show you the difference here in the get versus post. Request with the help of a figure. Yeah. So here you can see this image. See, whenever we are communicating over the get request, for example, we have this website, test PHP. Okay, so whenever you are requesting any website, like any web page, so you will see the get request. Get request is the default request. Okay, but whenever you are requesting the post request, post is like whenever you are putting something, you are putting any input. For example, here you can see we have this login page here, and here I want to apply the username and the password here. So this request will go on the basis of post request. Post request is can hide your username and password. For example, let's say you are using the get request for transmitting the username and password, and this username and password input by the user, right? So whenever you are transmitting this request using the get request, your username and your password will be appear here in the URL. So your username and your password will be appear with the URL so that anyone can see your username and password, right? So that is
Yeah.
why, for the security reason, we use post request whenever we are applying anything, any username, any password, any phone number, any email address. Whenever we are filling any form, we use post request. And when
Okay.
we use get request, whenever we are normally transmitting, whenever we are opening any web page. So you can see the
Yeah.
difference here. When you open any website and when you fill any form using get request, your name, your email, and your password will be appear here. And that
Okay.
is not secure. That is not secure. That is why we use post request. In the post request, your username, let's say I'm putting the name here, the email here, the bank name or whatever, any password here. So that will not appear here in the URL. It will not
Mhm.
appear in the URL. That is why
Yeah.
I use post request.
Mhm.
Okay. So post request, whenever we are filling something like username, password, when we are putting the name, phone number, email address, whenever we are filling any form, we use post
Yeah.
request. When we use
Mhm.
get request, apart from form filling or any filling, we use get request for the normal web pages. We ordinarily
Okay.
use get request, or whenever we are filling something, form, email, username, password, we use post request. Is it
Okay.
clear the difference?
Yeah. Yeah. That's clear.
Okay. So that is why you can see here we have two types of request, get request. So whenever we
Mhm.
are getting, like whenever we see, this is a get request of this web page. It is a
Yeah.
HTTP web page and it is a get request and we are getting login.php. This website, this you can see login.php.
Yeah.
Okay. So in this page, you will see HTTP and the host here. It is like a get request.
Yeah.
And first you will see the URL, the
Mhm.
HTTP version, the host here,
Mhm.
and
Mhm.
the connection here, which is keep alive, the user agent here, the accept here, and then we have some encodings here. Okay.
Yeah.
And you can see the full URL here. Then it is the request. When you click on the login page, you are sending this packet. You are sending this packet that I
Mhm.
want the login page fetch from the server.
Yeah.
And then we have some packet in the middle here. And here you can see we have the HTTP OK page. Okay, and the
Mhm.
size you can see is 1308 bytes. It is the
Yeah.
size of the packet. So
Mhm.
OK page means we are having the OK, which means we are having this web page. We are having this web page, which means we have the client, we have the server, and the
Yeah.
client is, whenever the client is sending the request, the client is requesting for the login page, this page.
Yeah.
Okay,
Yeah.
it is requesting for the login.php. And then we
Mhm.
receive the response from the server side, the web page. Web page means the coding here, which means if you right click here and you check the page source, you will see this part. So whenever you are requesting, they're requesting for this particular source code. Because what is
Mhm.
web page? Web page is a combination of coding, right? HTML, CSS, JavaScript. So whenever we
Mhm.
are requesting for the web page, we are requesting for the coding, like HTML page. The same you can see here. This is
Yeah.
all coding here. The same coding you will find here. Okay. Is it clear? So
Yeah.
in the
Yeah.
response, we have server Nginx, which is the server used by the server. The
Yeah.
date here, the content type, which is HTML web page. You can see it is
Mhm.
a HTML web page
Okay.
and some other information like it. Okay.
Mhm.
And then we have the actual source code. Now this
Okay.
is HTTP. That is why you can able to see this source code. If it is HTTPS, you cannot see. Now you have this at here. Now we have this post request. In this post request, I am filling this form here, username and password. Okay. If you
Yeah.
wanted to see, I'm filling this request. In the HTML form URL, we have this admin and password is 12345. So we can able to see this username and password in the clear test because of it is a HTTP, not HTTPS. Okay. With
Mhm.
some other information, like the user agent is Mozilla, okay, the browser information, the content information, and some other simple information. And it is a post request. And then we receive the response, which is 302 found. Like the username is not incorrect. So that is why it is just sending me the code, which is 302 found.
Mhm.
Means this web page only. When I apply this username and when I click on login, so this username and password is not correct. So this will launch me. This will just show me this web page only. Okay,
Yeah.
so that is a 302 found is not the correct username and password. So it is again sending me the get request. And then we have some egg packets and so on. Then we have some retransmission packets during the terminating the connections. Okay.
Yeah.
So it is a simple HTTP communication, and we can able to easily analyze because it is a HTTP or unencrypted. But when it is encrypted, then how we can analyze? Okay, that is the case. Even let me show you some more this part, which is the statistics of the HTTP. So you can click on the statistics. There are like 4 types of statistics in the HTTP. You can click on this HTTP. First, we have this packet counter. So when you click on this packet counter, this will count the number of requests within like how many requests are of 200, okay, how many requests are 400, how many are 404, and so on. So you can see total number of HTTP packets we have 56, out of which 200, okay, like the web page which have loaded successfully are 2 web pages. 30 found 1 web page. 400, which packet contain 1 error packet is 400. 404, which is 1 packet. And the rest packets are search packets. Post packets is 1. Get packet is 3. So you can see it will show you the summary of your how many packets are of which response code, of which HTTP response code.
Yeah.
Okay, then we have this timings and so on. This is packet counter, which is very helpful to analyze. Then second, we have this request here. In this request, you will notice which request is under which request, like which web page is under which particular URL. For example, here you can see we have one URL, a root domain, which is this one. Inside this website, I have requested for these 3 web pages: first web page, second web page, and third web page. So this will show you like URL. Inside the URL, how many web pages, how many files you have requested. So you can see we have requested 4 web pages. One from user info, one from robot.txt file, and one from login.php.
Yeah.
And rest web pages are from this website. Okay. So let's say you are requesting for the Amazon.com. So Amazon.com is a root domain. Inside Amazon.com, how many web pages you have visited, that will show by this request web page. Okay. And how many packets containing of this particular request. Okay. Then after that, we have third is load distribution. It is again same as the request here. It will show you in terms of IP addresses. That's it. Like we have requested, this is the first IP. Inside this IP, we have this 3 pages of something, okay, and one is error page here. Okay. Which is 3 web pages has been loaded successfully without any error, and 1 web page contain error here. Then we have this HTTP request by server. So these are the requests by the server, which contain 52 packets. 4 packets are from this website, rest packets are from this website. And this is the request by the HTTP host, which is the client request for the HTTP. 4 web pages are from the client side, and rest web pages are from the server side. So it is showing the load distribution, how many web pages are from the client side, how many web pages are from the like how many HTTP requests from the server side, and how many HTTP requests from the client side. That's it. That is in terms of HTTP only. And last, we have this request sequences. It is like in sequence. Like first, which web page you visited, second, which web page you visited, and third, which web page you visited. So it is showing in sequence. So first I click on this website. Okay, login.php. Then I click on this user info. Then I again click on this login.php, and then so on. So it is showing in sequence. Like let's say you are browsing the Amazon website. In the Amazon, which product you click first? Let's say this product. So this will take you to this product web page. So that is the URL. It will show in the second URL. Then after this product, which product you click again? It will move to it will take you to that particular web page. That is the URL here, and so on. It is showing the sequence. At first, which link you click, second, which link you click, and so on. So it is like a sequence. Okay, which link the user click first in the sequence, and how many packets are of which URL. Okay, it is like in sequence. It is very helpful whenever you are analyzing the malware, or whenever you are analyzing the packet, like any troubleshooting in the HTTP. Okay, so this is very helpful. You can see like what is going on in the sequence and how many packets are of which URL. Okay, is it clear this much? The statistics.
Yeah, that is clear.
Okay. Then apart from this one, we can use protocol hierarchy or this endpoints and convolutions and packet length for the HTTP also. So these are some part of the statistics which can be helpful in every sort of packets you are analyzing. Okay.
Okay,
Now
yeah.
we can move to HTTPS, like how we can decrypt the HTTPS traffic. So first I will show you in the Windows, then I will show you on the macOS or the Linux. Okay.
Yeah,
See,
yeah.
whenever we are analyzing the HTTPS traffic, you will not going to see anything because that is all encrypted. So how we can see the like HTTPS traffic? So first we have to decrypt it, and for decrypting we have to follow some steps. So
Yep.
these are the steps which are written here. See, first step is this one. You have to close all your browser. Okay, so first you have to open your machine. You have to close. This is on the Windows. Okay, you have to close all your browsers. Okay, let's say you are running the Firefox, Chrome. So close all your browsers. Secondly, you have to create a file. Create a file on desktop or anywhere. File name should be ssl-key.log. For example, this is my file. This one. ssl-key.log. This is my file. Okay, on the desktop. You can create anywhere you want. Okay, so this is my file. First, close all your browsers. Second, create an empty file. You can right click, click on new, and click empty file with the name of ssl-key.log. Okay, this is my file name.
Yeah.
Is it clear?
Yeah,
So,
yeah, that's fine.
second thing is, after creating a file, you have to open your environment variables in your Windows. You have to search for the environment variables. Open it, and here you have to click on this environment variables, this option. And there you have to you have to create an entry here. Okay, you have to click on new here, new, and there you have to apply a name. So variable name should be same. So that name should be SSL key log file. Okay, all in capital letters. Then variable value. So this is a value where you have to apply the path of your file, where your file is located. So you have to click on browse file and move to the location where your file is located. So my file is in the SSL keylog. This is my file. Okay, this is my file. For now, it is an empty file. Okay, it is an empty file. So you have to enter the path of this file and then click on OK. So here, this is my path. Okay, you can see SSL keylog file, and this is the path of my file.
Yeah.
Okay. Then click on OK. After this one, and click on apply and click on OK. This is environment variables. Now your file has been added. Now what you have to do, you have to verify the location from the step 2 is created. So what you have to do is, after adding your file on the environment variables, for now your file is empty. Now how you will verify that everything is okay? You have to open the browser. Okay, open any browser, search for any website, any kind of website. Let's say wireshark.org. Okay. Let's say you can open any kind of website. Once you open any website from any browser, minimize your browser and check out for this file. When you open this file, you will find some logs of your browser. Okay, you will find some logs. If you are finding any logs, then you are doing everything okay.
Okay.
But if you don't have any logs in the file, restart your machine, then again open the browser, then browse any website, and then check for this file. If you found any logs, then everything is okay.
Yeah.
But if you don't find any log, then again remove this file and do this again. Okay. But in many scenarios, you will find some logs in your file. Once you find the logs, now this is a log file. This contains your website logs, mainly your HTTPS logs. Okay. And every time you browse any website, this file size will keep on increasing. For now, you can see my file size is 2.32 GB. So whenever you browse websites, HTTPS website, this file will keep on containing your logs. Okay. And after that, open the open your Wireshark. Here in the Wireshark, you have to open the edit references. Now you have to add your file here. Okay, let me show you my file. You have to open your Wireshark in the Windows. And there's an option in the edit preferences. And there's an option of protocols. In the protocols, you have to search for TLS. TLS, which is Transport Layer Security. Here you have to click on this pre-master secret log file. And here you have to click on browse and apply your path of your file, which is ssl-key.log. Means you have to add your file here. Okay, you have to add your file here. Once you add your file here, you have to restart. You have to click on OK. Okay, you have to click on OK, and then restart your machine, your Wireshark. Restart your Wireshark, and then you will see your HTTPS traffic in your machine. Okay.
Yeah.
This is how the entire process works, and this is how you can able to decrypt the HTTPS traffic. Okay, let me show you the HTTPS traffic. And in the Wireshark, you can search for HTTP2 for the HTTPS traffic. So I don't have any HTTPS traffic in this file. So let me open any other file. So this is the process you have to follow for decrypting the HTTPS traffic. Okay, the same steps are applying here. You have to close your browser first, create a file on desktop with the name ssl-key.log, add in your environment variables, then start your browser, browse any website, check for the logs, then open the file Wireshark, add your file in the TLS layer in the protocols, and then start the Wireshark capturing, move to any HTTPS website, and then there you will find the decrypted HTTPS traffic. Okay. This is how you can decrypt. This is for the Windows. And if you want to automate this entire process, then you can copy this particular thing. This is a batch strip. So you can open your notepad. You can copy this one and paste this part of code in the notepad and save your file with the help of batch. It is a batch file. Okay. Yeah. So and then you can run that file and you will find this entire process to be automated. But don't try this in the Windows because sometimes it may throw an error. Okay, so in the Windows, try this manual way only. And in the Mac OS and in the Linux, use these commands. In the Linux, copy this one and just replace your file name with your location and file name, and then start the Firefox. In the Mac OS, same steps. Okay, make sure to change the SSL keylog file path and replace the Firefox with your own browser, whatever you are using. Okay. Yeah. So this is for the Mac OS, this is for the Linux, and this is for the Windows. Is it clear?
Yeah, that is clear.
How we can decrypt? Now we can check out the HTTPS traffic. Maybe we have some traffic here. So we don't have. So what we can do, we can open the file here. In this, we can search for HTTP2. No traffic at all. Let's see this main file. Now we can also start the live capture. Okay, let's see.
Okay. Yeah.
If we can have any HTTP. So let me browse any HTTPS website. We have this website. We have this website. We have any HTTPS website. Let's see this one. Okay. So now let's see some traffic, some packets. They like lots of packets. So let's see in this file, do we have any HTTP to traffic? Yeah. So here you can see this is all HTTP as traffic, which we can able to see because of the decryption. So here, to move this. So we have the source and this destination. So now what we can do, we can filter on the basis of any particular communication. Let's say this one, Google APIs. So we can right click and we can apply the combination filter TCP. So in this here, you can see this is the first packet. And then here you can see we are just, here we have some app packet here. In this, then we have some communication of like transmission of some TLS packet, which is a encryption extension. And you can check it out. Maybe it is a certification packet here. It is a certification packet. Then we have some app
Okay.
packets. Then we have some again certifications going on. After this one, we have the HTTP packets. Okay. System is magic here, and it is like it is providing the version and some information of the HTTPS, like some settings, which is like used by the the source and destination together. Okay, like on what kind of information or what kind of like window size, or we can say any other information, they will share the data. Like the same kind of parameters they are going to use. Then with this header here, here you can see we are requesting. It is a post request. It is a post request. Okay, in this we are requesting for this service update to and this one, and it is a key here. What kind of key it is? We can check it out. You can see it is a header. Still, if the traffic is decrypted, we cannot have the full access to the information. Okay, like just like in the HTTP, we have the full access for the username, password, everything. In the HTTPS, still we don't have the access. Why? Because let's say we can decrypt the traffic of the HTTPS, but the applications are also using their own layer of encryption, so that we cannot decrypt. Okay, so if you wanted to see the username, password, that we cannot, because sometimes the website uses their own encryption level for encrypting the username, passwords, and cookies, and so on. Okay. What we can see is the usernames, sorry, the URLs, and so on. So here, we have information. It is a header post. Authority is this one, which is Google APIs. And it is like some API traffic. We have the service here. I think it is some API here. Okay, we have some information of some API ID. So you can see, we can see the API ID in the plain text. So you can use this API ID for applying any attack that we can.
Okay.
It
Yeah.
is a Chromium. This is a updater we are using. And some other information like header information, encoding information, some browser information, and so on. Same as we can check out the data here. Now this contains the real data, which is all encrypted here. You can see it's data which is all truncated and encrypted. So these are all, this is the data here. So data is actually encrypted here. So we cannot check out the data. Then we have some settings window here. So this contains some settings like some Windows update, Windows settings, and so on. So this packet contains some Windows settings, which is sent by the server to the client. Then we have the settings here and so on. So in this TCP, go away packet is mainly for like disconnecting. Okay, this is for uh, it is go away packet is like we no longer wanted to communicate. That is like terminating the connection. That is a go away packet here. So in this particular traffic, HTTPS, we don't have any higher like access to the information. And rest, it depends on the application we are analyzing. It can be any application or any website. Okay. The main thing is we can simply analyze the, like we can decrypt. And even we have one more feature here in the Wireshark, which is in the statistics in the HTTP too. We can check out some HTTP kind of packets. So we have some few packets in the HTTP. Let me stop the capture because it is keep on capturing. So here we have this type is 143. So these are all HTTPS packet types. Windows update, this is for updating the window size. Settings, these are for making the changes. Okay, for like adjusting the parameters during the communication. This is reset stream. This is ping. And this is headers. These are for the containing the header information. Go away packet for terminating and the real data packets. Ping is for checking if that particular session is still we can say is still like alive or not. That is ping here. So we have these few types of HTTPS uh, packets there, which we can see in the Wireshark. So in the with the help of statistics, we can check which packet is of which like type. Okay, and then rest you can see the encryption packets, the the handshake packets of TLS, or some data packets and so on.
Okay.
The same mechanism we can use here in the display, like for analyzing the display. Delays.
Yeah.
And same now here packet loss is again same. The same mechanism you will going to use for analyzing the packet loss, which is sequence number and ACK number. Okay. Because HTTPS is working under TCP. We can analyze the packet loss and we can analyze the packet delays. Is it clear? The same mechanism. Here, please.
Yeah, it's clear.
Okay. Now, rest we can check out the packet HTTP3 traffic. Let me check out if any live traffic we have on HTTP. Yeah. So these are all live traffic of the HTTP. Yes. So you will find the same information in every traffic. The same HTTPS information, the same kind of packets, which contain either magic packets, header packets, data packets, like handshake packets, and so on. Okay, you can see. Now we can see the HTTP 3 packets. Just give me a second. Okay, just allow me a second.
Yeah.
Yes. So at last we can analyze the HTTP 3 traffic,
Okay.
which is same working on the QUIC protocol. Even when you analyze the HTTP 3 traffic, you will find that the HTTP packets working under QUIC are making the connection. They are establishing the connection. Okay, so how we can find that packet? Let's analyze any communication. This one. So again, they are all sort of encrypted. So we cannot actually analyze the real traffic. So what we can do, here you can see we have this packet here, which is initial and some handshake packets. You can see. So these are all handshake packets, which is transmitting between the receiver and client. So you can see these are all encrypted, and these are all like providing the encryption as well as the establishing the connection. Okay, so these are some IDs here, which you can see these are like same IDs for the same sort of packets. Okay, so this is S means source ID, and D means destination ID. Okay, so you will find the same ID in the entire communication. So you can know which packet is of which communication with the help of this ID. Second, crypto and PKN numbers are, these are packet numbers. So if you wanted to analyze the packet loss here, so you can check out the packet number here. Okay, so we have this destination ID, source ID for keeping the track of the packets, like which packet is from the which communication. And secondly, packet numbers are for keeping the track of the packets. Okay, then with this padding information, some crypto information. Okay. Then more else, what we can do here is, this is packet number 1, 2, 3, 4, 5, and this is second packet, and this is third packet, which is, this is the response, this packet is the response of the packet number second, which is this packet. And you can see it is an ACK packet, which means this packet is the request packet, and this particular packet is the acknowledgement of the first packet of this packet, second packet. Same as you can see, the third packet is the acknowledgement of this particular packet. And then we have this 4, 5, and so on. So again, you can see we cannot see the actual data here. So they are all like, encrypted. So we cannot see the actual sort of data. But we can analyze here the packet loss with the help of packet number. And packet delays are not very common here because they are working under UDP. They are not packet loss, packet delays are not common. But yeah, packet loss we can analyze. Packet delays are not common. And then with this transaction ID, rest everything is all like sort of encrypted here. Okay. So you will going to see the initial packet, the first packet, which is like simply like a same packet. Then you will going to see the handshake packets, the source ID, destination ID, and the packet numbers. And rest, all information is encrypted.
Yeah.
Is it clear?
Yeah. Yeah, that is clear.
So HTTP 3 is like under development. So yeah, we can, if you want, I will share a resource for this HTTP 3 headers, like what it actually contains, and the definition, or we can say the meaning of each and every header of the HTTPS, HTTP 3, as it is a new protocol. Okay, so I will share a resource.
Now the normal HTTPS traffic, they are using HTTP 2, not 3.
Sorry?
So, I mean, the main difference on HTTP 3 is like they're using TLS version 3 or something like that, 1.3 or something like that.
No, they are not using TLS. They are using HTTP 3 is using QUIC protocol, not TCP.
Oh, okay, yeah. So,
TCP, HTTP 2 using working under TCP. HTTP 3 is working under UDP on QUIC protocol. And more else, you can see here, actually it is a HTTP 3 traffic, but above you see TCP, this QUIC packets. So HTTP 3 is working under QUIC protocol, and QUIC working under UDP. Same as we have this HTTP 2. HTTP 2 is working under TCP.
Yeah.
But Quick protocol is more advanced than UDP protocol because it is like taking the features of TCP as well as UDP also.
Okay. Yeah,
Like
yeah.
for fast transmission, it is taking for UDP feature, and for the packet loss, congestion control, and for the encryption and for the connection establishment, it is taking TCP features.
Okay. Yeah. Yeah. Correct.
So I will share a resource for the HTTP3. So you will find the headers information there.
Yeah. Yeah.
So I think that's it. We have completed the entire syllabus of Wireshark. So do you have any doubt up to here? Any question?
So far, I'm okay with it.
Okay. And see, if you have any doubt, you can revise it. You can take your time. Okay, you can revise all the sessions, all the files. I will share it. After the revising, like if you have any doubt, anything you can share me, like you can ping me on WhatsApp in the group, and I will arrange a doubt session for you. Okay.
Okay, that would be great. Maybe I have next week I'm doing some packet captures and I will be doing Wireshark a little more. So I may get some questions I may come back to you.
And if you find any problem in the network as well, you can share it with me.
Okay, yeah.
And before leaving, you can put a review if you want. If you find this training useful, then you can put a review on the Google reviews. Okay, I will share the link.
Yeah.
So you can put whatever you want, and
yeah.
So thank you so much for your time. And if you find any problem, any doubt, you can ping me on WhatsApp. Okay, anytime.
Okay. Yeah, of course. Thank you very much, and thank you very much for your time for teaching me.
Thank you.
Okay.